אז בהרצאה הקודמת התחלנו לדון בנושא של סכימת טורים. היה לנו והצגנו את הרעיון של שנקס שעבד עבור טור מתחלף, זאת אומרת טור שהסכום שלו פעם מחמיץ מעל, פעם מחמיץ מתחת. אוקיי, אז עכשיו בהרצאה הזאת אנחנו נמשיך בנושא של סכימת טורים. בשלב הזה בואו נדבר על מצב שבו הטור הוא מתכנס לאיזשהו ערך שקראנו לו L, אבל מתכנס אליו באופן בלי את הטור שמתכנס ל-L בצורה כזאת. כן, מתכנס אליו מצד אחד ולא מחמיץ אותו פעם למעלה פעם למטה, אלא מתכנס אליו בצורה כזאת. לדוגמה, הדוגמה הקלאסית זה הטור סכום מ-n שווה 1 לאינסוף על 1 חלקי n בריבוע, שהוא פאי בריבוע חלקי 6, ואנחנו יכולים לראות, כן, הוא מתכנס לפאי בריבוע חלקי 6, אם אני זוכר נכון, כן? אז אנחנו מעוניינים בפונקציית זטה של 2, אם אתם, כן? ואנחנו מעוניינים לסכום אותו. עכשיו, אם אנחנו סכמנו את כך וכך איברים הראשונים, אז ההחמצה היא פחות או יותר אינטגרל על 1 חלקי n בריבוע. נגיד סכמנו את 5 האיברים הראשונים מ-n לאינסוף, שזה הולך כמו 1 חלקי n, שזה החמצה שיחסית היא גדולה, ואנחנו מעוניינים להאיץ את ההתכנסות של הדבר הזה, ולשם כך יש לנו שיטה שנקראת אקסטרפולציית ריצ'רדסון. כן, עכשיו סתם לידיעתכם, ריצ'רדסון היה, או שקודם אני אסביר את השיטה ואז אני אסבר לכם קצת על ריצ'רדסון. מה שריצ'רדסון הציע זה לעשות שוב מודל של ההתכנסות, והמודל הוא ש-Fn, זאת אומרת אם סכמתי את n גדול האיברים הראשונים בטור, אני מניח שזה הולך כמו 1 פחות, כמו L, פחות, או ועוד, לא משנה, כי זה יכול להיות ועוד a חלקי n, ועוד b חלקי n בריבוע, ועוד וכן הלאה וכן הלאה. כמה שתרצו, כן? אז לדוגמה, המילה הטכנית להגיד את זה, ניקח ריצ'רדסון עם איבר אחד, כן? זאת אומרת, ניקח את הדבר הזה. אוקיי? הדבר הזה אומר שאני מניח ש-Fn שווה ל-L ועוד a חלקי n, ולכן Fn פלוס 1 יהיה שווה ל-L ועוד a חלקי n פלוס 1. מסכימים? כן? וכש-n הולך לאינסוף הדבר הזה ילך ל-0 ואני אשאר רק עם L. אבל אם באמת אני יכול לעשות את ההנחה הזאת, אז מפה יוצא לי ש-n כפול s שווה ל-n כפול l ועוד a, ומפה יוצא לי ש-n פלוס 1 כפול s שווה ל-n פלוס 1 כפול l ועוד a. אתם רואים? כאן. ועכשיו אני אחסיר את המשוואה העליונה מהמשוואה התחתונה, ומה שאני אקבל זה, כן, שוב, אני לוקח מינוס של זה, פלוס של זה, נחבר אותם אחד לשני, מה אני מקבל? ה-a וה-a מצטמצם, אתם רואים? ומה שקיבלתי זה ש-n פלוס 1 s פחות n s, זה n-sn, זה n פלוס 1 sn פלוס 1, כן, כמובן, זה לא אותו סכום. זה שווה לדבר הזה פחות הדבר הזה, כלומר ל-L. כן? אז זאת הערכה שלי בריצ'רדסון הראשון, כן? אם אני משתמש בריצ'רדסון בזה הכי פשוט, כן? זאת הערכה שלי לסכום. כן? אני מחשב את ה-Sn איברים הראשונים, את ה-Sn פלוס 1 איברים הראשונים, כן, אז נגיד ב-1 חלקי n בריבוע, טוב, אז תעזרו לי. אז S1 זה 1, נכון? ומה זה S2? S2 זה 1 ועוד 1 חלקי 2 בריבוע זה 1 ורבע, זה 5 רבעים. אוקיי? אז מה יהיה הערכת ריצ'רדסון הראשונה הזאת? מה שאני אקבל זה 2 כפול 5 רבעים פחות 1 כפול 1, זה שווה ל10 רבעים פחות 1, שזה נכון?
כן.
10 רבעים פחות 1 זה 3 חצאים. כן? כמה זה פאי בריבוע חלקי 6? מישהו יכול לבדוק?
כן.
אז בינתיים בואו נעשה מה יהיה S3 בריצ'רדסון?
1.64.
אוקיי, לא רחוק. כן? מה יהיה S3 בריצ'רדסון? זה יהיה 1 ועוד 1 חלקי 4 ועוד 1 חלקי 9. כן? אז 5 רבעים ועוד 9. זה אומר שחלקי 36 זה יהיה לי...
49.
מה?
49 חלקי 36.
49, רגע, 5 רבעים, אז 5 כפול 9 ועוד... לא, כן?
כן, 5 כפול 9 ועוד 4 זה 45.
ועוד 4, כן. 49 חלקי 36. ולכן הערכת ריצ'רדסון הבאה על בסיס שני אלה תהיה 3 כפול 49 חלקי 36 פחות 2 כפול 5 רבעים. כמה זה יוצא?
.583.
1.583, שכמה אמרת שזה פאי בריבוע חלקי 6?
1.644.
כן? אוקיי. אז זה ריצ'רדסון בקירוב של 1. עכשיו, נעשה עכשיו את זה, ריצ'רדסון עם האיבר השני. כן? מה יצא לנו? יצא לנו Sn שווה ל-L ועוד A חלקי N ועוד B חלקי N בריבוע. Sn פלוס 1 שווה ל-L ועוד A חלקי N פלוס 1 ועוד B חלקי N פלוס 1 בריבוע. ו-Sn פלוס 2 יהיה שווה ל-L ועוד A חלקי N פלוס 2 ועוד B חלקי N פלוס 2 בריבוע. אוקיי? אופס. מה?
מבקשים לעבור לאנגלית.
אוקיי, let's switch to English. אוקיי, בסדר, נעבור לאנגלית. Let's switch to English. So, we have these three equations for the next Richardson approximation. And now, wait, yes. Okay, so now let's multiply this by n squared. So we have n squared Sn is n squared L plus Na plus B. You see? And now the next equation will be n plus 1 squared. Sn plus 1 is n plus 1 squared L plus n plus 1 A plus B, and the third equation is n plus 1, n plus 2, sorry, n plus 2 squared Sn plus 2 equals n plus 2 squared L plus n plus 2 plus n plus 2a, sorry, plus b. Okay, now what should I do in order to get rid of the coefficients a and b? Because my goal is to make a connection between partial sums and the actual limit of the series L. Okay, So what should I do to take care of, to get rid of the A and the B? With a little bit of thought, you will understand that I have to take plus 2 of this, minus 1 of this, and minus 1 of this. So first of all, from the B we have minus B and plus 2B, which is 0. For the A we have NA, n plus 2A, so together we have 2n plus 2, and from this we have in a minus sign, and from this we have 2n plus 2 in a plus sign. So it will go away.
Yeah.
Okay? So at the end of the day, our second Richardson approximation will be like that, n plus 2. Okay, n plus 1 squared Sn, okay, plus minus Sn plus 1, sorry, minus n squared Sn minus n plus 2 squared Sn plus 2. That's a weighted sum of the right hand side. This is equal to, now we have n plus 1 squared, here we have L, you see, and we have n plus 1 squared minus n squared. Okay, so let's write it. We have n plus 1 squared, which is n squared plus 2n plus 1, minus n squared from here. I have 2 of this. Right? This is coming from the n plus 1 squared times 2.
Okay.
Minus n squared times 1 minus n plus 2 squared, which is n squared minus 4n minus 4. So the 2n squared cancels out, and the 4n cancels out, and what we have is minus 2. So we have to take, this is equal to, okay, so plus plus minus, right, equals to L over 2. That's it. Okay, this is the second Richardson approximation.
Plus? The n plus 2 is in a minus. No?
What? Again?
Why the n plus 1 is in
כפל הכל במינוס.
I multiply everything by minus 1.
okay.
Okay? And so let's try to implement it, right? For this. Now we have S1, S2, and S3. Okay? So this will be the 1, 2, 3. And what Richardson is suggesting to us is to take the S1, okay? Just remember that, okay, now we are taking all 3, right? And we are taking S1 times 1 squared, so S1, so 1, minus S2, which is 5/4, times, wait. Yes, okay. Times n plus 1 times 2 squared, so times 4, okay, plus S3, which is 49 over 36, times what?
9.
Times 9. All this should be multiplied by 2. What's the answer?
I think it should be divided by 2. Why multiply by 2?
No, this equals to L over 2.
No, but you have there minus 2 times F, right? On the right side of the equation. Everything you cancelled out, it was like minus 2 times L.
This is the coefficient of L.
Okay, so the coefficient of L is
The
minus.
coefficient of L is minus 2.
So why here it's 1/2?
Ah, sorry. This is 2,
Okay.
and now I have to
Okay.
take 1/2 of this. Sorry. So 1/2 of this. Sorry. How much is that?
לא. 4.125.
Hmm?
4.125. זה לא מתקרב.
So we made a mistake. Wait. L. Okay. First of all, we have 1/2. Okay. N squared times Sn for 1 is 1.
Yeah.
You agree?
Yeah.
Now we have minus. Wait. You have 2. Right? Because we multiply this by plus 2.
Dad,
So on and so
this is my question. Why there is no -2? This was
So.
my question.
Okay. So we have a 2 here.
So
So now please calculate. Okay. So this is 1.625 that you can see is very close to the right answer. Whereas naively we have 49/36, which is not close to the answer, and this is much closer. Right? And you can continue either by calculating more terms using the force. Now, can you tell me what will be the force? I mean, if I'm taking Richardson with A, B, and C, how it will look like? Okay, extrapolation from 2 examples. It's very easy.
So you need to take +3 and then -1.
L1 of the first Richardson is n plus 1 Sn minus Sn plus 1 minus Nsn. L2 is 1/2 times n plus 2 squared Sn plus 2 minus 2 n plus 1 Sn plus 1 plus Nsn.
I guess no, it's not
Yes.
n. It's n squared.
Your guess?
I guess it's n plus 3 cubed minus 3 n plus 2 squared, maybe minus n plus 2 squared s n plus 2 plus 3.
You need to divide by 3 factorial. Yeah.
Okay, you got it. You got it right. So it's like
כפל מקוצר.
it's, whatever. So a plus b cubed, but with this I mean the Pascal triangle coefficient. 1 1 1 2 1 1 3. Wait. So it should be a plus here and a minus here, of course. 1 3 3 1, and the next one will be 1 4 6 4 1, and so on and so forth with alternating signs, and you have 1 over n factorial to begin. Okay. So this is Richardson. This is Richardson. These are Richardson formulas. So just to let you know, Richardson was, as I told you last week, perhaps the most important physicist you didn't hear of. he contributed a lot to almost all branches of physics. Now Richardson was why he invented all these tricks? Because he was interested in weather forecasting. Okay, so he was the first guy to understand that if you have data about the temperature of the air, the density of water vapor in the air, and the wind velocity, pressure, something like that, right?
Pressure you can derive from temperature, no?
Yeah, that's right. So whatever. I mean, you there are 7 quantities you have to know, and if you know them, you can predict the weather. The only problem is that you have to solve 7 coupled nonlinear differential equations. And he got data from the Netherlands. They have one day they have some exhibition of balloons, and they measure whatever required for the weather forecast in different heights, and he had all the required data. The only problem was to do the calculation, and it was 1914 or something like that, and he got the data, and sooner World War I started, erupted. Yeah.
When was the first time the forecast told us to bring umbrellas in a sunny day?
Wait, it's more ridiculous than what you think. So Richardson was drafted to the army. However, he was Quaker, and the Quakers are not. They are pacifists. They don't serve in the army. So he was. They had some deal. He was an ambulance driver or something like that. Spent winters in the Western Front in France, and there he found they were living in a barn of a French peasant, where he had a stack of hay, and he was lying there all the winter with pieces of paper and trying to calculate, right? And so what he did was to calculate. He just numerically did it, right? He didn't know how to solve the equations, the 7 coupled the 7 coupled nonlinear differential equations. So he did it numerically. He defined delta t is 0.01 and started from the initial conditions. And his goal was to predict the weather for 6 hours. So he had data from, let's say, 9 o'clock in the morning and 3 o'clock afternoon. And he wanted to, based on the 9 o'clock in the morning, to calculate what will happen in 3 o'clock afternoon. He worked a year or so on that while being an ambulance driver in the West Front, and he failed. So after a year or so of calculations, the results he got were wrong with respect to the actual weather that was the things that were measured in the Netherlands a few years ago, before that. Still, after the war, he published a book with the title Weather Forecasting Using Numerical Computations or something like that. Nobody bought the book. I mean, it was one of the worst sellers of all times. And but he has an idea, right? After spending all this, and during that he invented all. En passage, he invented all these tricks in order to make his numerical calculations more efficient. So after, sorry?
10 non-important stuff.
Okay. So and nobody on earth was interested in his book, but in this book he put forward the idea of calculate using computers to make the process of the numerical calculations more efficient.
What year was that?
What?
What year was that?
1920. Okay?
So,
However, when he was speaking about computers, it was not what you have in mind. For him, computer was a huge arena, like, football or maybe basketball stadium with many people sitting there and calculating things. And there is a group of few people in the middle that are acting like the CPU and are telling people what to calculate. And so in this way they will be able, by having all kind of parallel algorithms to calculate, to predict the weather. And of course, as I told you, nobody perhaps took it seriously except of one person, who was John von Neumann, the famous mathematician. And von Neumann read the book of, or at least was familiar with the ideas of Richardson. And after World War II, they did have computers, because they need computers to calculate all the things that have to do with neutron transport in active media, right? Which is to develop the nuclear bomb. And actually, when they started doing it in Los Alamos, the calculation, they did it the way Richardson recommended. I.e., they have collected all the secretaries and other people in Los Alamos, and they have one of them were adder, and the other one was multiplier, and so on, and they have pieces of paper moving around, and they calculate. But then after the war, they started to have real things that were computers, and it cost a lot of money. And they needed to justify. I mean, they want the government to pay for the research on computers. That at the time, every computer was in the size of 5 times this room, right? And so they want money from the government, and they have to justify it somehow. And so the trick of von Neumann was to justify the research in computers by telling the government we are going to predict the weather. I mean, that now we can implement the ideas of Richardson and have a way for efficient and reliable.
There were some weather forecasts before.
I have no idea how they did that, but it was not based on solving equations, whatever it.
Because I know in World War II there were many weather forecasts operated by both sides.
Not focused. I mean, there were reports of the weather. I mean, it's famous because the German submarines, the U-boats, were reporting the weather at their location every morning, and then it was like something that what's it called? Turing implemented in order to deceive the Enigma code, but that's another story. So what von Neumann told the US government, I mean, it was tricky. He told them like that what we are now developing is a new type of warfare, weather warfare. So we will be able in the future, for example, to color the North Pole in black by pouring coal or something like that, that it will become black, and then it will generate horrible tornadoes that will wipe out the Soviet Union. This was the idea. And
also destroy humanity. Also destroy humanity, but it doesn't matter.
Sorry?
But also destroy humanity, but it doesn't matter.
No. I mean, it will be focused, right? I mean, if you can play with the weather, I mean, whoever you like, however you like, you can do that. This was the idea of von Neumann, and they got the money and started developing weather forecast as we know today, and discovered that it cannot work for more than 4 days. Right? It have a very limited scope. And the question was why? The scope, I mean, very limited scope. The question was why, and then in the 60s, Lorentz discovered that the problem is that the equations that they were trying to solve all the time were chaotic. Which implies, and this is the butterfly effect, that very small changes in the initial conditions may change completely the answer, so you cannot implement the brilliant idea of von Neumann. But anyhow, so this is Richardson. Okay, so both Richardson and Shanks are method to sum converging series. The only problem is that the series may converge very slowly, so these are convergence accelerators, right? You use them and you accelerate the convergence instead of having to calculate 10 or 20 terms in the sum, in the partial sums. You can calculate only 3 or 4 and you get a reliable answer. Okay, this is part number 1 of our discussion in series summation, how to sum convergent series. And the answer is, you simply sum them one by one, but there are these tricks that allow you to sum them even faster. Yes?
We discussed about convergent series of slowing sums, of slow sums, but if we take the slowest sum, I can think about a sum of a log. How do you do that? If I want the general solution to sum of logs, actually I have it. It's a multiplier, not doesn't matter.
Okay, I don't really understand, but let's continue. So now let's speak about a more interesting problem, which is the summation of diverging series. Now, what's the definition of a diverging series?
There isn't the limit for the סכומים חלקיים, for the part.
i.e., in Hebrew or in King's English,
כאילו אי אפשר, על הסכומים החלקיים אין גבול.
okay. Every series that do not converge is a diverging series. Okay? So let's write a few examples. For example, A1 plus, okay, 1 minus 1 plus 1 minus 1 plus 1 minus 1 is a diverging series. Okay? Another example, B, 1 plus 2 plus 3 plus 4 plus 5 is a diverging series. Another example, C, 1 plus 1 plus 1 plus 1 plus 1 plus 1, diverging series. Another example, D, 1 plus 0 plus 1 plus 0 plus 1 plus 0 plus 1 is also a diverging. No, I wanted it with alternating signs. 1 plus 0 minus 1 plus 1. Wait. Plus 1, yes. Plus 0 minus 1 plus 1 plus 0 minus 1 is a diverging series.
So you just took A and added plus
Oh.
zeros?
Okay, good. I waited for this question, of course.
It's his idea.
Yes. So you are complaining that I am just I'm just wasting your time and מבלבל לכם את המוח by taking a series and adding zeros every now and then, right? Okay. So the first point you have to realize is that in order to make this series to that series, you have to use commutativity and associativity.
Okay, but it's like
Right?
normal addition.
Now, to use commutativity and associativity in infinite series, even in converging infinite series, is a problematic thing to do, and it is, in general, it is not allowed. For example, take the series of 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 and so on. This is what? What is it? Ln 2. Good.
You can make it however you want if you change.
Exactly. If you allow me, now, note the following thing. First of all, what is the sum of 1 plus 1/3 plus 1/5 plus 1/7 and so on? What is the sum? It converges to what?
זה סכום על 1 חלקיהם של כל המספרים האי-זוגיים.
Who cares? It's infinite. Right? Just approximately, it's the integral of 1 over 2x plus 1. So it's going like ln of 2x plus 1 that goes to infinity when x goes to infinity. Okay? Similarly, minus 1/2, minus 1/4, minus 1/7, 1/6, and so on. Also, this is infinite and this is minus infinity.
So you can shape it however you like.
What?
So you
Exactly.
can shape it however you like.
So now, if you want me, this series, I want it to sum up not to ln 2, but to pi cubed over 57. Okay? Whatever you like. The trick is, I'm starting from 0. How much is 5 cubed? Over ln 4. Right? I will start at 0. So this is pi cubed over ln 4. Right? I will start from 0 and I will take from this series terms as much term as I want until I will collect something that will exceed pi cubed over 4. Then I will take from this series terms until I will go down. And then I will take from this series terms until I will go up, from this series terms until I will go down, and so on, and this will converge to whatever I like. So by changing, by commuting terms, right, I can get whatever answer that I want. Because this series, although it is converging, it is not, how do you say that? מתכנס במידה שווה.
לא, צריך להתכנס בהחלט, לא במידה.
בהחלט, נו, איך אומרים את זה absolutely. It is not absolutely convergent. Right? So I can get whatever I like. So this series and this series are not the same. They were the same if it was an absolutely converging series, then it was the same thing. But since this series is not, every series that is not, for every series that is not absolutely converging, I can use commutativity and associativity to get whatever I like. Okay? Good. So, what are we doing? So suppose you are a physicist and you get such a series. Okay? The question is what to do. one possibility is to jump from the roof because we don't know what to do. But there is another possibility. The other possibility require. Okay, let me just tell you, for example, explain what one can do. One can use Euler summation. Now, Euler summation implies that I'm taking this series. This series is a sum over an from n equals 0 to infinity, where an is, okay, an is what? This series, a. What is an? Minus 1 to the power of n. Okay? And this is a diverging series. So the idea of Euler is, let's add here x to the n. Now, if n is smaller than 1, I can write it as minus x to the power of n, again from n equals 0 to infinity. Now if x is 1/2, this is the converging series, right? If x is 0.99, it is also a converging series because the x to the power of n is going down exponentially, right? So I can sum. What is the answer of this sum? This is a what?
2 under C.
2 under C. תלכו את זה באנגלית, לא משנה. Geometrical series, something like that. So what's the answer?
1 לחלק 1 divided
1
by
over 1 plus 6.
1 over 1 plus
minus 6.
this thing, or plus minus 6.
No,
So
it's minus 6. So it,
what?
it's
Minus-
minus
So
6.
it's minus 6, so it's 1 plus 6. Right. Good. Now, we started with the sum. So how do I get back this sum of minus 1 to the power of n?
You just put x equals to 1.
Great. If x is 1, then I will get back this series.
But you
But
can.
now I'm taking x equals 1, and what I will get is 1/2. Great.
But you can't because it's only depends if on the borders the
radius
the series converges. It depends on
The
the
radius
radius.
of-
So you see, it's 1 over 1 plus x, and it converges on the edge to 1/2.
But how do you prove it converges on the edges?
On
What?
the same note, you can say that b is equal to minus 1 over 12 because z of minus 1 is minus 1 over 12. It's like,
Wait. We will reach that. Okay? So this is called Euler summation. Now, first of all, please I just want to make sure that you understand. Okay, so let's make other examples of Euler summation. I'm now just trying to exercise our ability to implement Euler summation. Okay? So let's try Euler summation for the sum. What do I want? I have the series 1, 2, 4, 8, 16, and so on and so forth. Okay?
I had 0. Z of minus 2.
This is sum from n equals 0 to infinity of 2 to the power of n. You agree? I don't know what this sum is doing, but now let's try Euler. So the Euler sum of this is sum from n equals 0 to infinity of 2x to the power of n. Right? I multiply it by x, and I'm taking it to the n power. Again, this is a geometric series whose answer is 1 minus 2x. Now when I'm taking x equals 1, I will get minus, so 1 over 1 minus 2, which is minus 1. So this is converges to minus 1. Euler convergence to minus 1. See? Let's take another example. Okay, what about 1 plus this one, C? The series C. Okay? So what we have here? We have sum from n equals 0 to infinity over 1. So instead, we are going to have
1 to the power
over 1 to the power of n, right? The Euler of this thing will be sum from n equals 0 to infinity of
x to the power of
x to the power of n. The answer is 1 over 1 minus x, and now when we take x equals 1, what we are going to get?
We got to get error.
Infinity. So under Euler's summation, this sum, C, 1 plus 1 plus 1 plus 1, is going to infinity, whereas the sum 1 plus 2 plus 4 plus 8 plus 16 is going to minus 1.
How do you know if you take x from the left or from the right?
What?
How do you know if you take from the left or from the right? If you take from the right, it's minus infinity. Like 1.01, 1.001. It's not
I don't
necessarily
understand.
infinity. It can be also minus infinity. The limit doesn't exist in x equal to 1.
But in any case it diverges.
Yeah.
Right? Okay, let's take another example. Where it is? Yes. Let's speak about D. What about D? Right? Let's Euler sum D. So Euler sum of D is as follows. It's okay. So when I multiply it by x to the n, I will get 1 plus 0 plus x squared minus x squared, sorry, plus x cubed minus plus 0 minus x to the 5 plus x to the 6 plus 0 and so on and so forth. You see? This is 1 x squared, x cubed, x to the 4, x to the 5th, x to the 6th, and so on.
You took every it's like
I just
it's
multiply
like
the nth term by x to the n. Okay? And this will give me sum from n equals 0 to infinity. Okay, let's take just the pluses. So I have 1 x squared, x to the 6, and so on. So it's x to the 3n minus x squared sum from n equals 0 to infinity of x to the 3n.
But
Do you
we
agree
just
with
said
that?
that we can change the order.
What?
We just said that we can't change the order.
Only when the series is not absolutely converging. But this series is absolutely converging.
How you have one and minus, you have pluses and minuses.
No, with x. If x is smaller than 1,
Okay.
for every x which is smaller than 1, this is an absolutely converging series. And according to the Geneva Treaty, I have the absolute right to change the order of the summation.
I don't think this is written in the Geneva Treaty, but
Because it is true, you say. Okay, fine. So, what's the answer? The first sum is 1 over 1 minus x cubed minus x squared divided by 1 minus x cubed. All in all, I have 1 minus x cubed, 1 minus x squared. And now I have to take x to 1. What's the answer?
0 divided by 0.
Okay, and what we are doing when we encounter 0 divided by 0, we apply to Mr. L'Hopital and take the derivative of that, divide it by the derivative of that, and we are going to get 2/3. Thank you very much. See? So this is the Euler of this.
So how do you calculate series B?
Minus
How do
1
you-
over 12 z of minus 1.
What?
How do you calculate series B?
B. Okay, I can try.
Minus 1.
Let's try series B. Euler calculating series B. So series B will give me under Euler sum of n x to the n from n equals 1 to infinity. Right?
Yeah.
Now this is ddx of the sum of this is x ddx of the sum over x to the n from n equal 1 to infinity. You agree with me?
Yes.
Because when I take the derivative, I will get the n here, and then I multiply it by x. Okay? Now what is this sum? This sum, if it is from n equals 0 to infinity,
it's
right, it's 1 over 1 minus x,
mhm.
but I have to subtract the first term, which is 1.
1.
Right? So this is minus 1. So what I will get is 1 minus x times 1 minus 1 minus x.
It's x minus.
So I got
X.
an x over 1 minus x.
And then you
Now I have to take the derivative with respect to x of this, and I will get
and you'll cry.
what?
And you'll cry. No, it's not such happened.
I have to take the derivative of with respect to x of this. So I will have 1 over 1 minus x. This is the derivative with respect to this x, right? And now I have the x, and I have here 1 minus x squared, and I have a minus.
Minus minus, it's plus.
No.
Minus minus. Right. Okay? You are taking responsibility, right? So I have 1 minus x squared, and here I have 1 minus x plus x, so I have 1 over 1 minus x squared. And I
then
should
you
multiply it
by
by x, so I have x over 1 minus x squared at x equals 1, which is
It should be infinity.
infinity.
But what's the difference if I take the series 1 over n to the x and then substitute minus 1 after the main expansion? Like to take the original definition of the zeta function.
Wait. You understand that? Okay, this is Euler summation, right? And Euler summation
Yeah.
allow us to calculate a few of the series, right? To calculate some series, and do not allow us or give us diverging result for other series, right? I mean, it's not a crime for a series to diverge, even under Euler summation. It's not a crime to diverge, but some of them do not diverge and some of them do diverge.
So Euler's summation is only for geometrical series.
It is easy to implement it for geometrical series. Okay? Let me show you another trick.
You can
So,
implement.
clearly, Euler summation will not save your life. I mean, Euler summation, you multiply every term here by x to the n, right? Where x is smaller than 1. So it's an exponentially decreasing function. If the terms in the series are exponentially increasing, then you can't use Euler summation. I mean, Euler summation will not cure the exponential increase. So what to do when you have exponential increase of the terms of the series? Then you are implementing a different method. Not due to Euler, but due to Borel. Borel with how many R's? Yeah, Borel summation. So the trick of Borel is to notice, first of all, that the integral from 0 to infinity of t to the n e to the minus t dt is 1. Is what? What is this integral?
Gamma function. Gamma n
Of-
plus 1.
Which is
N factorial.
n factorial. Okay? So 1 is 1 over n factorial, the integral from 0 to infinity of t to the n e to the minus t dt. Okay? Are you happy with that?
Very happy.
Now the trick is, what do you mean? Yeah. Now the trick is, every series of the form sum from n equals 0 to infinity, say, of an, I can write as the sum from n equals 0 to infinity of 1 times an. That's for free, right? And now I replace 1 by z. Okay? So what I have is a sum from n equals 0 to infinity of 1 over n factorial integral from 0 to infinity of t to the n e to the minus t times an dt. Okay? Until now I did nothing. Now I will switch the order of integration and summation.
You can do that?
Of course. Of course I can do that. The only question is whether or not it will give the correct answer, but I can do. Right? And what I will get is this integral from 0 to infinity of e to the minus t dt. And now I have the sum from n equals 0 to infinity of an over n factorial t to the n. Now, why this is better than Euler? Because now we have here, instead of having x to the n that decreases exponentially, now we have something that decreases like n factorial.
How did you took t out of the integral?
What?
How did you took a t
e
out
to
of
the minus t is in the
כאילו עדיתי הוא בצד
אה.
ימין. בסדר.
אוקיי, לא הבנתי.
that it is. Okay. So for example, again, I'm going to series A. 1 minus 1, 1 minus 1. This implies that here I will have sum from n equals 0 to infinity of minus t to the power of n times n factorial, which is what?
E minus
E to the minus t. And then this will be integral from 0 to infinity of e to the minus 2t, this one and this one, dt, which is exactly 1/2, which is what we got from Euler. Okay, so at least the Borel and the Euler gave us the same answer.
But,
So Borel is stronger than Euler?
Yes,
but if you take
the Borel is working even when Euler is not working.
but if you take series C, for example, you still get infinity no matter what.
If you take series 3, for example, C, this one,
C,
yes,
you still get infinity
Yes.
no matter what.
right, I agree. I mean, okay, now, I should remind you, okay, so now I should remind you two things. Yes, so one of them, we have tried before, right? We have implemented Euler to series B, and what we got?
We got infinity.
We got infinity, right? Series B was
Infinite series.
gave infinity under Euler. I believe that also under Borel. I didn't try, but I guess so. However, when we have implemented Euler to series A, what we have gotten?
We've gotten
1/2,
1/2.
right? So if you purchase this, right, idea, let's call it S1, and S1 is 1/2, okay? Now let's define S2 as 1 minus 2 plus 3 minus 4 plus 5 minus 6 and so on. Okay? And what I want to do, I want to add to this series S2 another series S2, which is 1 minus 2 plus 3 minus 4 plus 5 and so on. And if I add these two, what I will get?
S1.
S1.
You see, 1 minus 2 plus 1 minus 1 plus 3 minus 2 plus 1 minus 4 plus 3 minus 1 and so on and so forth. So 2 times S2 equals to S1, which is 1/2. So S2 is 1/4. Right?
Yes.
And now,
I think.
now I will speak about S3, which is 1 plus, wait. Yes. 1 plus, what do you want to have as S3? Yes. S3 will be B. So it will be 1 plus 2 plus 3 plus 4 plus 5 plus 6 and so on. And I will subtract S2. So 1 minus 2 plus 3 minus 4 plus 5 minus 6. I subtract, so S3 minus S2. What is the answer?
It's
1 minus 1?
0.
0. 2 minus minus 2? 4. 3 minus 3? 0. 4 minus minus 4? 8.
8.
5 minus 5? 0.
0.
6 minus minus 6? 12.
12.
So you see we have 4, 8,
No.
12,
Plus
Plus 12, not minus 12.
plus 12.
Of course.
4, 8, 12. So at the end of the day, what I have is 4 times
S3.
S3. Right? 4 times 1 plus 2 plus 2. Okay? Which implies that 3 times S3 is minus S2. So S3 is minus S2 over 3, which is minus 1 over 12.
What?
Right? Which is a famous result that the sum of all the integers is minus 1 over 12.
But it cannot be, right?
Why not?
Z of minus 1.
I know that
It's-
it's
This.
I think that this argument was included in the famous letter that Ramanujan sent to Hardy and
So does it say
It
right?
is mathematics. You sure it's mathematics? It's not just tricks that. It's
Okay.
Not,
so now, first of all, you have seen that the Euler summation and this trick is called, I mean, the name of the big thing is zeta function regularization. Right? This is zeta of minus 1. Right? Zeta of minus 1 is minus 1 over 12. Now, a few points. First of all, you may ask, how could it be? I have 1, 2, 3, 4, 5. It's an ever-increasing function. How could it be
yes.
that we end up in
The
minus 1
negative.
over 12?
yeah.
Answer. To the extent that the word an answer, you have to think about it in the complex plane. Right? In the complex plane, infinity is a point. Right? The complex plane is a sphere, and infinity is a point on the sphere.
Of course.
So now you think about it, you started, you see, this is infinity, right? You started here at 0, and you added, tak, tak, tak. And you go all the way to here, and you end up here, right? This is the complex plane meaning of this result. Okay? And it had to do, you know, with analytic continuation of functions and blah, 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 blah. All that. Good. Now, the important point is to understand what is, we as physicists, I mean, okay, you encounter a problem in which you have to sum all the integers, like in Casimir effect. Yes? And you find out that that the answer, I mean, and you are saying, okay, so the answer is 1 over 12, minus 1 over 12, right? What does it mean? It means the following. Now we have to understand something. There are functions, right? Functions are abstract quantities, Platonic ideas that are living in heaven with God. Right? These are functions. What we see when we are writing sin x, right? Sin x is the name of a function.
Yes.
Right? And now when you are saying sin x is 1 minus x, it's x minus x squared over 6 plus x to the 5 over, who knows, 120 and blah, 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 blah. This is a way to calculate the function. The function is, as I said, this is the name of the function. The function is an abstract quantity in heaven. And this is one of its galuyot. Revelations. Right? This is a revelation of the function. Okay. Some revelations are nice to us in the sense that we human beings may calculate the actual value of the function by going through this series and summing up terms. But the world is not so nice to allow us to do that in any case, right? For example, if you have the function 1 over 1 minus x, this is one revelation of the function. Now if you have this revelation of the function, 1 over 1 plus x, this is one revelation of the function, right? It's an algorithm of calculating the values. And if I'm asking you what is the value of this function at x equal 1, what is your answer?
2.
1/2.
1/2.
1/2.
Great. Very simple, right? However, in some other, by solving, very complicated theory of physical phenomenon, you can find out the Taylor series of this function, right? Which is what?
1 minus x.
1 minus x plus x squared minus x cubed, and so on and so forth. And if I'm now asking you what is the answer for x equals 1, right, you will tell me, well, I have the series 1 minus 1 plus 1 minus 1 plus 1 minus 1, and this is a diverging series. So you see what's the problem? The problem is that this revelation of the holy function is not a good one for us, poor human beings, right? We cannot use it to calculate the actual number, right? Somebody asked us, what is the value of this function? I have a physical scenario for which the answer is that, and I want to know what's happened if I put, I don't know, the initial velocity is 1 in whatever units, right? I want x is the initial velocity. So if the initial velocity is 1, what will be the who knows what? and this is the answer, then I am calculating it very easily. But if I worked hard in a perturbation theory and I got this answer, then I don't know what to do. You see?
Yeah.
And unfortunately, there was a discrepancy between the angel that has, have the task of planning the physics of the world before creation. And, I mean, he did his work fantastically, but he didn't care about the idea of allowing human beings to understand physics, right? And as a result, many physical problems that we attack, what we get is such theories that diverge when we plug the correct numbers, right? But this has nothing to do with the physics itself. The physics itself is fine. The electrons know where they're supposed to go, and they go in the right direction. Everything is fine. The only problem is that we as human beings, sometimes we cannot see the function, a revelation of the function that allow us for calculation. We can only see revelation of the function that diverges, meaning that do not give us any reasonable answer when we calculate it term by term. And now, all this witchcraft of Euler summation, Borel summation, zeta function regularization, and all these nice words, all these black magics, are tricks that may allow us to guess the correct function. You see? We don't know, I mean, we have only this series. We have only 1 plus 1 . We don't know, so what what Euler is telling you is that actually the real function is that, and now plug x equals 1 and you are completely happy. You see? That's, this is the meaning, the physical meaning, right, of these regularizations. These are black magics that allow us to guess the actual function, the abstract thing in heaven, from the series that we have. However, until now, I have showed you only how this black magic works when you have a diverging series, but you have all the terms of your series. However, if you learn quantum mechanics, for example, and they show you how to implement perturbation theory, right? How many orders you have calculated in perturbation theory? Maximum 2, right? None of you, you calculated third order perturbation? No.
Why?
Okay. You calculated only what? First order perturbation, right? So I think, I told you, I think that Kondo got the Nobel Prize for calculating third order perturbation.
To what specifically you want to calculate a second order perturbation?
Second order? No. Second order you are doing a lot.
Yes.
But third order is something that, it's usually you have to dedicate a lot of time and effort to calculate third order correction.
Or a
Something.
computer.
What?
Or you get a computer.
It's not so easy. I mean, I think that for the most simple perturbative expansion, which I guess is a 5 to the 4 theory, they've calculated up to 7th order. And this required, a huge crew of Russian mathematicians or French mathematicians or whatever.
Kind of mathematicians.
Hmm?
Of what other kinds of mathematicians?
No. Only Russian and French guys are doing that. It's no. I don't know why, but anyhow. So in the generic case in physics, it's not only that our series is diverging. We don't have all the terms except of the first 2 or 3. Right? So now we need not only witchcraft, but black witchcraft, right? To grab a number and a reasonable assessment of a number from a series that, first of all, we know that the series diverge, and we also know, and we also do not know the general answer for a term of the series. We don't have analytically the general term of the series. We only have the first few terms, like the first two, the first three terms in the series, right? So we cannot use Euler and Borel because these require all the series, and we have only the first three terms. We don't know what an is for n equals 5. Okay, so now we have, so Euler and Borel were and this zeta function regularization is a first level witchcraft for beginners in the beginning for beginners in the art of black magic. And now the second term is Padé approximation, which is the real thing, which is how to sum diverging series when you know only the first few terms. Right? This is what we are going to do now. I don't think that we will have time for the Padé all the Padé analysis, but I will start by showing you something that at least can serve as a guide. This is not Padé, what I am going to show you, but some other in the spirit of Padé. We can think about it in general as continued functions. So now I want to translate a series, sum from n equals 0 to infinity over an. An, do I have a parameter? Yes, an x to the n, right? A general power series. I want to translate it to continuous function. To start with, let's speak about continuous exponential, right? So I want to write this as at b0 e to the b1x, e to the b2x, e to the b3x, and so on and so forth. You see what I'm doing? Sounds crazy, right? So first of all, but please allow me to continue. So I want to convince you that there is a one-to-one relationship between the A's and the B's.
I don't understand. What exactly you're trying to do with this? How do you...
I want to find a function of this type that have infinite coefficient, b0, b1, b2, b3, that will be exactly equal to this series.
Why?
Because it's a nice example.
Okay.
So what I'm doing? Okay, first of all, my goal is to illustrate how to make a one-to-one correspondence between the series of the an and the series of the bn. Okay, let's start. Let's start with, okay, let's write this as b0 times e to the b1x. So I assume that I can neglect all the series from here up. Okay, which implies that I can write now, and I assume always that x is small. That's why I can neglect all these guys, right? And so what I will have is that this is equal to b0 times 1 plus b1x. You see? So maybe I will write it as 1 plus b1x plus half b1 squared x squared. Okay?
Now, what is b0 times e to the b1x times e to the b2x? No, times, to the power of e to the b2x. This will be b0 e to the b1x times 1 plus b2x plus 1/2 b2 squared x squared. You agree with me? I keep only terms up to x squared. And this will give me b0 times 1 plus b1x times 1 plus b2x plus 1/2 b2 squared x squared. Is that enough? If I want only terms that are up to x squared, is that enough?
No, you get another x squared from the next.
Yeah, okay, great. Plus 1/2 b1 squared x squared. You see? This is, so, I mean, this will be an expansion to first order in x. This will be an expansion to second order in x. Of course, for third order in x, I will have to take into account only the one level up, right? So, if this is, so up to second order in x, I have b0 plus b1x plus b1 b2 x squared. This is from this times that. You see? This I don't need because this will give me x cubed. And then I b0, sorry, because I have the b0 is outside here. And now I have plus b0 b1 squared x squared over 2. You see? So I have a map. A0 must be equal to b0 because this is the coefficient of x to the 0. Now, what is A1?
b0 b1.
A1 is b0 b1. What is A2?
כל המנגנון שבאחריו.
b0 b1 b2 plus b2 squared, b0 b1 squared over 2. And I can continue, of course, the expressions will be more and more complicated, right? But I can continue with that and have a one-to-one correspondence between the A's and the B's. Not only that, convince yourself, I think it's very easy, that every term here, I mean, if I have A0, I can calculate B0. Now I know B0. So in the next equation, I know B0, so I can calculate B1 very easily. Now I know B0 and B1, so in the next term, I can plug B0 and B1, and I will get B2 very easily, and so on and so forth. In every step, I have to calculate only one extra parameter, which is a B of the index that corresponds to the A.
It will always be linear equation.
Yes. Yes, I think for the B,
Yeah.
not for because B1 is known. For the new B, I guess it's a linear equation. Good. And so this is a representation of a series by continuous exponentials. Okay? Now you are asking yourself why someone should be idiot enough to represent a series by a set of continuous exponentials. Okay? And here is the answer. There is
specific case, I will take extra 5 minutes because the lecture started in right. I'm speaking about e to the x, e to the x, e to the x, e to the x, and so on. So how do you describe this in terms of that?
B not
All the b's are
so
1.
B2.
All the b's are 1. Right? And some bored person that have way too many extra time discovered that this is equal to the series n plus 1 to the power of n minus 1 divided by n factorial x to the n. Okay? So, of course, I didn't prove it to you. You are welcome if you want to show that. I have no idea how to do that. You have to find some sort of, recursion relation. But this is true. This continuous exponent is equal to this series. According to, it's not equal, it's parallel to this series. Term by term. Term by term. Okay? Now, here is the question. What is, so if I have this is real x, and this is the imaginary part of x, what is the radius of convergence of this series? Right? This is a Taylor series. What is the radius of convergence?
Take the limit of the a and goes to infinity.
N goes to infinity. When n goes to infinity, n plus 1 is more or less n, and n minus 1 is also more or less n. So as n goes to infinity, what I have is n to the power of n divided by n factorial. However, what is n factorial when n goes to infinity? Stirling formula tells you that n factorial is n to the n e to the minus n. Okay? So this is n to the n divided by n to the n e to the minus n, which is e to the n. So the general term of this series, as n goes to infinity, is converging to ex to the power of n. Now, what's the condition for this series to converge?
e to the x less than 1.
Ex must be smaller than 1 enough. So what is the radius of convergence?
1
One
over
over
e.
e.
1 over e. Right? So if x is 1 over e, the series diverges. And of course, because this is a Taylor series, its radius of convergence is exactly determined by that. So the radius of convergence of this series is this circle of whatchamacallit, of radius 1 over a. Okay? However, the mathematician that was bold enough to show that was also able to show that the radius of convergence of this continuous exponent is, if we have minus e here, it is going like that. Everywhere in the purple heart, right? So if you take a point here, the Taylor series diverges, but the continuous exponent converges. Of course, within this circle here, they both converge to the same number, right? But here, the Taylor series diverges, but the continuous exponent converges. Okay? So it's like an analytic continuation. It's an analytic continuation by means of a continuous function, where here it's a continuous exponential. So again, what do I mean?
I mean that a physicist may suggest that this is, so I got this from a perturbation theory. I want to calculate the answer when the x is a -1, say, right? And what I am doing that, and then I am saying, okay, this is a bad representation of the holy function in heaven, right? And I should use, instead of that, I should use this, and this will supply me the right number, because this is a good, nice, a friendly representation of the same holy function.
Yeah, but how do you calculate the series e to the x?
X is equal e to the minus
Now,
x.
because if x is, I mean, because I can truncate it, because these approximants are converging. I mean, okay, so in principle, right? And not that I did it. I just grab it from a lecture by Bender, but this is what I mean. It delivers the idea. Okay. Now, in the next lecture, next week, we are going to use another. This is called, as I said, continuous exponential, but the actual trick that we are using in physics is not continuous exponentials, but continuous fractions. Right? And this is called Padé approximation that I will show you next.
בגדול נעשה קצת מבוא לסטוקס, אני לא בדיוק הולך על פי המערכת הגול שלי.
אתה עושה את התרגול בעברית היום?
אלא אם יבקשו אחרת, בגדול יש לי מערכת הגול באנגלית, אז אני יכול להרגיש קצת יותר בחופשיות לדבר היום בעברית, כן?
כי היחיד שמדבר אנגלית לא נמצא היום?
כן, ויש לי מערכת הגול. אתה יודע, ההקלטות זה מותרות, כן? גם המערכת הגול, אני חייב לעלות אחד מהם בשנה הזאת, כי אנחנו בכל זאת בשנת מלחמה וזה, אז יש הקלטה אני יכול לעשות בעברית, ויש מערכת הגול באנגלית. אז נכתוב פה תופעת סטוקס, חרא של טוש. איך אלו? טוב, תופעת סטוקס, מעולה. בגדול אני אתן מבוא לתופעת סטוקס, ואז אני אנסח את זה פורמלית. אני חושב שמדוגמה פשוטה אחת אתם תבינו את הגישה ולמה העניין הזה חשוב. אוקיי, אז בואו נסתכל עכשיו על סינץ' של x, נרשום סינץ' של z, כי אנחנו עכשיו לא ראיתם את תופעת סטוקס בהרצאה?
כן.
אוקיי, מעולה. מה שווה סינץ' של z? סינץ' e
בזה, כן, בזה.
z מינוס e ומינוס z חלקי 2. עכשיו אני רוצה לתפוס את הפונקציה הזאת, נקרא לה f של z, פונקציה f של z שלנו, לתפוס את ההתנהגות האסימפטוטית שלה כאשר z בערך מוחלט הולך לאינסוף. אוקיי, ברור מה שאני מנסה לעשות? מעולה. אז עכשיו בואו נסתכל על הדבר הבא. אנחנו יודעים ש-f של z כאשר ריל z הולך לאינסוף.
טוב, ביקשו באנגלית.
Okay, so let's switch to English. Let's write the right side and left side actually. So now we will want to talk about the asymptotic behavior of the sinc function. No. Okay, we will actually sinc will be another good example. Okay, so we will do sinc after that, just to check your understanding. And so we present the sinc function. It's the sum of e to the z and minus e to the minus z divided by 2. And we want to find, for now, just to demonstrate the Stokes phenomenon, what happens when real z goes to infinity. Okay? What happened there? What would be asymptotically?
It depends on if the limit
It will be e to the z divided by 2, approximately, right? I can write actually that thing. What that mean?
Asymptotic too.
at the go to.
Yeah, actually, when
Like the
real
limit
z,
of,
that is why Stokes phenomenon is important, because when you're talking on complex numbers, they're not 1D numbers like the real numbers, they are 2D numbers, right? So you can approach to a point with a lot of paths, right? So Stokes phenomenon, talking about the validation of our asymptotics in the limit to a point, that point can be at infinity. For example, just to declare a notation, I can approach the infinity with some argument theta. Okay? Just to clarify what is the notation, it's the argument with theta that is that infinity. Okay? Minus that infinity. Or you can just add pi here. That is the same. Okay. So when you're trying to do asymptotics in the complex number, you need to define how you go to infinity. Sometimes you have asymptotics that is valid for all approaches to infinity, but sometimes you have some problems for your asymptotics. For now, we looked on the sinc. What happened when real z, when we take the path real z that go to with real z that go to negative infinity, what we will get?
minus
That
to the minus
this
the-
will approach 0, but that's still approaching in absolute value, actually. I will mean
תעבור לקוש.
infinity, right? So it's not valid. There is some sort of a phenomenon. In the past they called that a paradox, but we know that after a couple of years they solved it. I think, who were the ones that solved this? I don't think Newton, but I'm not sure. Stokes, I know that, okay, Stokes is the one that solved that, but I'm not sure who's the one that found that problem. That's what I meant. Okay. So now after understanding the problem, we can actually say that for, okay, let's say here, for sinc z, for z in absolute value goes to infinity, we get that it's approximately goes like in arg z less than pi over 2, it goes like what?
e to the z divided by 2.
E to the z divided by 2. And the other case is when arg z is, okay, I don't want to write it with bigger than that. Let's write it with pi over 2 arg z, then 3 pi over 2 e to the minus z. Minus. Right. So what we are getting is we have two different asymptotics, right? By the way, you talked about anti-Stokes lines. Okay, that will be a new thing in the tutorial. It's also another definition we will see. Okay. So that is the asymptotic behavior. We see there is a problem, and now we want to know how we solve it. So you saw it already in lecture. What is the solution to that? It's actually written on the board. Divide the plane to different regions. Okay, for example, for infinity, what you're doing in the Sinch case.
From 0 to pi over 2.
Yeah, from 0 to pi over 2. Actually, let's write the real axis with that. That is the real axis, that is the imaginary axis, and that is the Stokes line. Right? That's all. You have a nice picture in my tutorial notes I made. ChatGPT made, okay. Let's be honest, but okay. So let's define it formally and maybe more rigorous, so we will be able to talk about that on a general case. Okay, so we understand the phenomena, why it's important to understand what happened in the limit, but we will have to define and deal with the case a little bit carefully and to generalize it for every solution in function. So consider a function f of x f of z, okay, and we will define her. We will define the domain in the complex plane. Okay, and assume f of z is asymptotically summing on n a n z e to the phi z, right? And let's say we say asymptotically, we need to say for what is the path, what is the approach. When z is approaching z0. Okay? Now we just need to clarify the path, the region that allowed for the path, right? That is the solution for Stokes phenomenon. And they need to maybe define carefully what is phi of z and a of z, phi n of z. So what is phi n of z? The leading behavior function. For example, if you solve your ODE, if you solve your ODE with e to the s method, you get S0, right? The first order. Okay, not leading behavior, it will be zeroth order, because leading behavior is all the terms until it's when you approach it goes to 0, right? So first order 0, actually 0 order behavior e to the 0 goes like that. So example, and we're talking about something in the exponent, so S0 will be 5 in the case of solving all these. And AN Z, the other terms, what they can be? The other sum of, for example, S to the N and not equal to 0, because that is already 5. So the less dominant terms the less terms. Okay. It's in my tutorial, so I wrote amplitude function. And how we will define the Stokes phenomenon in that case. For example, in the sinh case, if we want to look on that in the ODE perspective, from which ODE you will get sinh? Y2 primes equal to 1, right? So, and the actual solutions at phi in this case, phi of z, is minus plus z. And here, what happened? Which equation we solved to get that boundary? For one solution, we get real z equal to 0 for one boundary. And okay, that actually defines the path. Should be there. Real z equal to 0. So we say that there is something with, and with z we can switch it to phi, right? Because real z is also minus z, so it's phi. So the generalization here, it's a little bit more trickier, but okay, so the Stokes line will be real of phi n equal to 0. But when you want to talk about something that the asymptotic behavior changes, you actually want to talk about the comparison of the leading behaviors, right? So here's the Stokes line for phi n, but if we will want to be more specific, if you have m and n that is not equal to each other, the Stokes line will be real of phi n minus phi m equal to 0. That will define the Stokes line. And by the way, when phi n and phi m are linearly independent, dependent, they depend on each other, right? That thing will be actually equivalent to that thing. For example, here we have dependency between phi 1 and phi 2, okay? Plus and minus. And setting that equal to 0 is equivalent to say z minus z equal real of that equal to 0. So, and what is actually interesting here is when you're summing on all of those terms, what will be the dominant term, right? You can see that I will prove something very quick for two terms, that if we have A1, it's pretty much constant as compared to phi. E, so we will assume it's constant for our case. Phi 1 of z plus A2 e to the phi 2 of z. We can take out one of them. Let's take out e to the phi 2. Okay, let's say that in our region, let's set it to be arg z of something, okay? Phi 1 will be the dominant, is the dominant. Okay? Therefore, when we're summing those stuff, we will take phi 1 outside, e to the phi 1 of z is equal to a1 plus a2 e to the phi 2 minus phi 1. And here we see that for that thing to be 0, maybe we will explain it intuitively. It's like here that the, let's see, okay. Now we can set that to be 1, because that is pretty much 0 as compared to the other stuff. Or let's be more careful, you can set that because of the asymptotics to be minus phi 1, and we just plug it in. A2 is negligible, that is negligible as compared to that, because that is times that, right? And we get A1 is, so we get that in the asymptotics. But we need that it will be dominance, and the switch between the dominance is coming in for real z equal real of the difference equal to 0. Why we care only on the real? Why we care only on the real? What will be e2 phi 2 minus phi 1 in absolute value?
1.
No. It will be e2 real of phi 2 minus phi 1. Okay? That is why it's interesting, because it's the transition when phi 2 will be more dominant than phi 1. We will get that will be positive, and therefore we can say that phi 2 is the dominant. If we say that phi 2 is the phi 1 is the dominant,
Why it needs to be the real part of phi 2 and phi 1? If you take, for example, if phi
yes,
2 and
I'm
phi
talking about the real part. Yes, that will be dominant. That's why we take in the real. Okay.
Oh, you say you want to look only on the dominant part.
Yes, that's what we said. Phi is the dominant part of the solution.
Mhm.
Okay. So, in the general case, we have a lot of phi function, and the actual interesting behavior is when each two, when we look on pairs of all solution, has the transition. Okay, and see which one is the strongest in each region. If you have 3 solutions, you need to check each pair, see which one is the strongest in each region. Yes. And it's depending only on the sign of the difference, right? Because
if
if
they-
it's big
What
a little bit, when we take z to infinity or to z0, I will have also a finite not example in this tutorial. You will see that the other stuff will be negligible compared to the other thing. Okay. By the way, if we have Taylor expansion or something like that that is well defined, continuous at that point, and pretty much approaching 0, it is not that interesting. If you have 2 asymptotics, now it's getting interesting, right? If everything agrees, it's not interesting and you don't have Stokes phenomenon. There are cases that it's Stokes phenomenon is not appearing. So let's do one example and then come back to anti-Stokes lines. For example, in Airy function, right? How Airy goes like fz, right? Times e to what? What is s0?
פלוס מינוס 3/2 הפוך
2 over 3 z to the 3 over 2. If I'm correct? Yeah, I'm correct. So we have 2 solutions. We need to take the difference and set it to 0 to find the Stokes lines. So what we will do is just set in z to the 3 over 2 equal to 0. That is for what?
60 מעלות, פאי over...
Yeah, well, we will do it rigorous. So what we have here is r to 2/3 and cosine cis, or let's be cool and write it with 3 over 2 e to the I 3 over 2 theta. Now setting e to the, it's actually the real part, and we will divide by r, so we will have cosine of 3 over 2 theta equal to 0, and what we are getting, like Oz told us, it's the 60-degree solution, or pi over 3, right? Minus plus pi over 3, so we get that theta, it's just arc z, need to be less than pi over 3. Okay, that is for the behavior that we want. That we want only one of them. We don't want both of them to be in our solution. So for getting one specific solution that we will be able to say Airy is going like something, we need to be in that region. For example, for that to be e to the 2 over 3 z to the 3 over 2. Okay. And for example, we know that another equivalent, totally equivalent solution to the Airy function okay, it will not be Airy, but it's actually, yeah, Berry will be the dominant. here, but the Stokes lines are still this. Okay, it's depends. For that solution, we get that. What I were about to say. Just a second. We want to say something that, okay, maybe L is going like fz times sinus of something. Let's look. Okay. 2 over 3 minus z to the 3 over 2 plus pi over 4. What is that? Where is that is valid? For the minus infinity solution, right? It will be oscillatory, and then you want to look when that will be right to estimate it like that. So how you will find that? You will use sinus, you will write it in exponent and just finding the zero of the real part in the exponent. We know that the solution will be just I times that thing, right? And then we will get the solution. It's not that horrible. And it will be, I think, the same stuff, but now because we did it on minus infinity, we will have to take the other part of the Stokes lines. Right? We have here the pi over 3 and the minus pi over 3, but now we will look on that. So that is the region that our estimation is valid. Okay. And the anti-Stokes line is basically the same stuff. The anti-Stokes line is basically the same thing, but now we will set the imaginary part to 0. Does someone know why? Why it's interesting to look on the transition of imaginary part going to 0? Of the difference, yeah, right?
Because you said so.
Not good answer? That means it has something interesting there, but okay. I will explain. When image of phi n minus phi n equal to 0, that means that there is no, if we will take, for example, we will have a loop on something like that, because those stuff are in the exponent, right? That thing will be actually equivalent to e to the re phi n minus in absolute value, right? Because we don't know which one is bigger, re of phi n. What is that? That thing will be always true, we think. But, or actually it will be always true, something like that. From what? אני אומר אי שוויון המשולש. Triangle inequality.
אי שוויון המשולש.
So it's actually when the solution you have the difference, it's actually, how will you say that? It's the only case when that thing equal to that. They have the most difference between each solution, and it's determined by the size of each expression. Okay, it's interesting because you want to look what is dominant, and we are humans, so we can't think about 2D numbers like the complex numbers. So speaking on real numbers in exponent is much more intuitive to us. So looking on the anti-Stokes line that defined by that, for that, on that path, that thing is valid. And that is the path when we have the most difference between the two solutions. How we will present that? We will look again on the sinh. What happened? What is the Stokes line for sinh?
Parallel
Anti-Stokes line.
to
Yeah,
oh, five.
theta equal to 0 is the anti-Stokes line. Anti-Stokes line. And here we get, let's write z x plus iy. So here we get e over x, that, and the other solution, write sinh of x. X is a real number. And here we can see that is the Stokes line, and e of x is the place in all region that the difference is the biggest, because here if we look on a circle for what theta that has the difference between the two solutions will be the biggest, it will be on the anti-Stokes line. So it's also interesting because in that area our approximation of saying f is going like one of the terms will be the best. So mapping, if you have a lot of n's, and mapping everything is a little bit of chaos, but if you have the possibility to approximate near one of the anti-Stokes lines, it will be the best. So it's important to know. For me, it's mostly technical to do that. It's just solving first year equation, right? Most of them you already saw in school. But let's do some examples, finishing that, and go on. So let's just write a summary, and then we will shift the boards and finish here. Yeah. Stokes line. Yeah. That is for real phi of n minus phi of m equal to 0. Anti-Stokes line imaginary of phi n minus phi m equal to 0. Okay? For now everything is clear. Everyone understands why the Stokes lines is important and the anti-Stokes lines is interesting. Thank you. Okay. So let's now do some examples. And I don't think I will give homework on that, but next week I will give homework on that topic and the next topic that Shnav will teach in the closed Wednesday. I think I will upload that in in Sunday for 2 or 3 weeks, just to give you time, but I'm not sure. I didn't decide. Okay. So example 1. Let's look on the e or I function. It's defined by that integral. We e to the minus about 18 4. That is okay. And one thing to note that okay, and we assume that, just for clarification, the negative real part is random. It's not allowed. You can mostly see why, because you have that point that will make a lot of problems that don't want to deal with. So we can say that theta, the argument of z, is much less than pi. Okay, and what we want to find the symptotic behavior of that thing. So how do we solve that? Something like that? How do we find solution to something like that? What will be the appropriate solution? We actually didn't study integrals, but you can maybe develop that in your own time. If no one sees that immediately, you can prove it, but okay, we will not prove it right now. That is 1 plus 1 factorial 1 factorial divided by z plus 2 factorial divided by z plus so on. Right? You can maybe see why you can do that with gamma function and adding 1, subtracting 1, and do linear combination of the integral. Or you want to be cool and do that with integration by parts, that is also a possibility. You can just take that integral, integrate on that, differentiate on that, and progress with that thing, and you will get that expression that is also valid. You will see when, in the end of the course, Satan will teach you the integrals. I will not be here, I will be in military. So, sorry. And
This
What-
is
what-
asymptotic to the IZ where? Z goes to infinity?
IZ square.
No, I mean, this is a proper equality or it's only asymptotic to...
That is proper equality.
Okay.
But we will want to discuss on what happened at the limits. Here, let's write the full summation. What will be also interesting is what is the radius on convergence of that symptotics. What will grow faster for given z? Z to the n or n factorial? N factorial, right?
Factorial, of course.
Right, so the radius of convergence is pretty much 0. And even that is only valid at infinity because it's a Lorentz summation, right?
Wait. You want to...
But okay, we will get to asymptotic series.
Which function is this? E to the I? EI?
EI,
EI is... Which function is this? This is the...
EI function.
EI function. It's not Euler function, right?
I'm not sure
Because
what is Euler function.
there is also
I'm
another
not sure
function.
what is Euler function. I don't want to discuss on Euler function right now. I want to continue, but okay. You can search on Google and read on it in your own time. I define the function here. So what will be the Stokes lines? Let's write the Stokes lines. Take another color. Okay, what will be the Stokes line? All the phi's are the same, right? So the only thing that is dominant is that term. We can look, and what is actually interesting to find Stokes line is just the real of phi in that case. That is real of z equal to 0. We get theta is pi over 2 plus minus. Therefore, Stokes line will be when theta is less than pi over 2. Will be that stuff. That is the Stokes line. And the anti-Stokes line, let's write in different color. I really feel like black pen, red pen, just to show the colors. Someone know who is it. Let's write it. Imaginary part of phi equal to imaginary part of z equal to 0. Get that theta equal to 0. Therefore, the Stokes line, what is it? Yeah, it's the real axis, but that is abandoned actually. So that will be, let's color that stuff. So the Stokes line area is that thing, and actually anti-Stokes line, ASL, is that stuff. Close to it, that is where the assumption of the asymptotics is the best. Okay? Because the difference between the solution will be the biggest. Okay? So, okay. Let's look on another example. Very simple. Sinh of 1 over z. What will be the interesting asymptotics?
It's 0.
At 0, yeah. It's more interesting than infinity. Going to infinity, it's interesting, but not that interesting because all converge, so it's boring. So let's draw the graph. Here what happened, okay, here it's actually the same. When you want to find, okay, let's do it more carefully. 1 over z equal to r squared z star, right? So everything we did already to find the Stokes line, for example, in this example, that is also just with plus, but it will be pretty much the same, right? because now we will have to search for real Z star equal to 0 for Stokes line. And
Real Z
for
star equals to 0, Z is a pure imaginary, right?
no,
Like-
it's the same. What is Z star? Real Z star will be cosine of theta equal to 0. So the solution to that is theta equal to plus minus pi over 2. So the solution for Stokes line, that will be our Stokes line, okay? And our asymptotics is valid here, okay, in the complex plane.
So what is the
And
anti-Stokes line?
The anti-Stokes line, it's still the same, because the imaginary part of Z star is sinus of minus theta equal to 0, so theta equal to 0. So we get, let's switch the color to confuse you. It will be that stuff, and here it's the best region for fitting the asymptotics. So, and why you can plug in and you will see. You have a question?
No.
You raise your hand. Okay. I think we can continue to asymptotic series. It's more interesting. And it will be okay. Let's write it there. Okay. Okay. So asymptotic series. Let's start in here. Series. Do we write this? Seven. Okay. Let's assume we have sum again of let phi of n be sequence of func in region, or let's call it domain D, subset of the complex numbers. Everyone familiar what is subset? Okay, good. Why? For example, solution to Stokes line is working in a subset of the complex number for our asymptotics, right? Okay, and we will assume and phi of n for f of z, we will say that f of z equal to sum of a n phi n if that is the for we need to say for which approach z going to z0 can be also an infinity, we will say that one thing that need to satisfy is phi of n plus 1 equal to phi of n, which is basically saying that phi of n plus 1 is negligible as compared to phi of n, right? Everyone? Okay. We can say that maybe more rigorous will be phi of n divided by phi of n plus 1 inverse when z goes to z0 goes to infinity. Okay, that is maybe more clear. And we will say that will be asymptotic expansion if, okay, if an such that will exist, blah 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 blah, unique, that is already coming from that condition, but we need that f of z minus the sum to n minus 1 of an phi of n z will be in order of phi n. Okay, I have mistakes in my lecture notes. It's supposed to be phi of n. See? It's the reminder, if you know, for example, from Taylor-Maclaurin expansion, it's the reminder of the summation. Okay? So that is the condition, and if those stuff are applying, one couple of things that we get, if those things happen, we get one an is unique. That's how I write unique? I'm not sure. Uniqueness of the coefficient, and we get that 2, the best, how will we say, for given z, for given z, we can find n of z to be the optimal point to stop, and it will be actually very easy to find because we know that is bound by phi of n, right? So even so that sum can be diverge, for given z we can find optimal n that is the best fitting for our case. It's a little bit counterintuitive because you're used to having something like in Calc 1 or Math for Physicist 1, you're saying for all epsilon there exists n such for large enough n, from there on that limit will be true, but here it's the opposite. If you see, I'm giving you z. I'm not saying for all z. I'm giving you specific z, and for that z, I'm saying that I will find the n that is optimal for convergence. It's like more function convergence. That is maybe Calc 2. I know physicists never heard of that thing. Function convergence. You know that because you know to take the limit on phi of n and see if something interesting happened, but there is a lot of formalistic stuff on function convergence when you in function convergence take the limit outside the integral, inside. That is maybe more close to those stuff, but here it's interesting also for physicists. So let's start giving some examples. And I think we will finish in about, I don't know, by the way, I didn't do all the examples in my tutorial for the Stokes line and all of those stuff because I felt it's you understand what I said there. It's okay, right? If not, you can read by yourself, but okay. So, example 1. What would be the first function summation that you know? A very nice one. You're all familiar with. Aviper really likes that. No. Now I'm upset. Generalize the geometrical sum. Taylor expansion. Right. For f smooth function, we can say that f of z is equal to the sum of f n 0 divided by n factorial, sum of all n's, z minus z0 to the n. That is a summation when z is approaching z0, right? For finite z0. And why here it's valid? Okay. We need to show that thing. And we need to show that thing. So that thing you already did in Calc 1 or 2, I don't care. That is from Taylor Maclaurin summation, so that maybe in numerics also when you try to approximate what? Yeah, the reminder, when you try to bound the reminder, you use that fact. It's well known already. I'm not willing to prove that. But that thing I will do to not say that is trivial, right? So phi, for our case, of n of z is z minus z0. Right, that is just constants. Right, that is a of n in our case. And therefore we get that phi of n plus 1 of z divided by phi of n of z equal to z minus z0, and when z is approaching z0, we get 0. Nice. From all directions, you can prove that. I'm not willing to. That is way too trivial. For you, Avishai, I'm choosing a delta equal to epsilon, right? In that case, you want it formally. Wait, you're not math major.
No.
Okay, too bad.
בשבילך.
For me. Okay, fair enough. So here,
Nimrod is a math major.
yeah, but he left.
He left.
So let's say now for, let's say, what is next? So let's look now on our example with I of z equal to e to the minus z divided by z, sum of n factorial divided by z to the n. Okay? We can say that actually I need to that's in, and I wrote in my lecture note, tutorial notes that the phi of n is just z to the minus n, but it's not right because how we define that is the sum outside. But you get the idea of I can do that and I can do that thing, and what is interesting is the thing that need to converge. So saying phi is equal to z to the minus n is okay, we're not mathematicians. The statement is correct. So but for now I will do it like that because that's how I defined it here. So that is a constant, that is not interesting. We're just interested in that stuff. And now what we will do?
The limit of n plus 1.
Oh, by the way, just a reminder that infinity e to the minus t. By the way, you try to see why that is right. If you integrate on that, differentiate on that, what you will get? From integrate that we will get minus sign. From differentiate that we get minus sign. Okay, now you see the minus cancel, and then you will get 1 factorial. Next time it will be 2, 3, 4. That is not changing. That will be each time give you another term, and that's why you get that. That is the end of the course material. But okay. So what will be the ratio between phi n plus 1 to phi n? 1 over z. So where it's valid, if z goes to z at absolute value, because we don't care about the direction, z can go to infinity, and that will be correct, because that will go to 0. So that is where our asymptotic series will be okay, converge, not converging in that case, but will be fine, because the only thing we want to estimate, for example, I of z, right? We want to estimate that, and in that mission we can do that by optimal truncation. Maybe I will give you in homework to do that. It's just searching for minima of the next term, right? It's not that hard. You just need to search for minima of n plus 1. By the way, why we do that? Because you can see very clearly from that we get that is bounded by that, right? So when that will be minimal, that need to be like that. When that will be minimal, that will be minimal, so that thing will be the closest. And who promises that will be a good estimation? Because, okay, that minima can be 1,000, and in not appropriate scales, who promises that will be small, right? That assumption, because that is the next term. It's small as compared to the other terms. Okay, you see the idea of that? So even if the sum is diverging, we get a sum that we sadly can't take the limit to infinity formally, but we are physicists, so we can do everything we want. But for a given z, we have some way to approximate our function. You see the uses of that, because we want to deal with asymptotics. Oops.
לא,
Nice.
ויהי חושך ויהי אור.
Okay.
איפה זה היה קודם?
זה לא היה.
לא, אבל תשאיר אותו.
לא.
Okay. Okay. So if you got some ODE from your physical problem, you want to estimate that, you can, in a lot of times that function appears, because if you will set
What is phi?
what?
What is phi? It's
Phi?
Pn.
I defined it here. It's this.
The function itself.
It's sequence of function and defined in domain D. Okay? And for example, that function appears a lot if you will do the substitution of t is equal to ln of something, you will get why it appears a lot, because it's very common type of integral. Actually, a lot of times, to make sure it converge, you have -1 here. And then when it's approaching to 0, it's actually analytical everywhere. So it's nice to know. Let's give another interesting example. I have the gamma function. It's nothing special, it's just the Stirling full, all the Stirling expansion. I wrote it, so it's very nice, you can use it. But I'm not sure, we did that, we proved the Stirling formula in lecture 3 when I did that last year. But Schnerb is doing things in different order. I'm not sure when we will do things with Stirling, but we will do. Okay, that also we like. Let's do that. Also, what is your favorite function?
אני אוהב סינוס.
Area of what? For sure Bessel function, right?
כן.
At which point? Bessel of nu? At nu secant of theta. Theta is just a parameter. It's a well-defined function as a function of nu, right? It's the nu Bessel function at nu sec theta. You have a lot of ways to show that, actually, from doing Fourier to the OD of Bessel and all of those stuff. It's easy to get some integral representation of the Bessel function, and when you taking it back to the integral form, you get an integral that asymptotically you can approximate it at that point. And that's how you get that scary thing. Oh, I wrote it with beta. Okay. All right. mu of tangents theta minus theta divided by 2 pi square root of 2 pi. By the way, from where that square root of 2 pi came? Exactly. An mu of n it's easy to prove with tools that we will study in the end of the semester, I think. Okay, that will be, in that case, phi n of nu will be 1 over nu of n, and we already proved something similar to that, that for nu approach infinity, it is actually asymptotic sum. By the way, an is well defined and you need to do the asymptotics in order to get them, but just the flex of writing the first order term of that Bessel function, it's very nice. We will have something like 3-4 ways to prove that thing. I know we got that thing in the test, in Kessler's test. Okay, Earth function is also a nice stuff, but I will not do that. Okay, one last thing for this tutorial. As you saw in that course, you will see a lot of names of functions, of random functions that mathematicians in the 20th century, just from boredom, or physicists that had a very unique physical situation, or mathematician with combinatorical, also combinatorics gave us a lot of functions and random numbers for some reason. Thought of, and you will see in that course all of them. So it will be actually very nice. And let's look on that thing. Y 2 primes, by 2 primes I mean d to dz, okay, in complex, will be z squared plus lambda squared times y. Let's come back to ODE, because ODE is always nice, right? In our case, lambda will approach infinity and will be a real constant. Okay? In homework, you will get lambda is constant. Complex. No. No. Ozzy is already willing to do that, but no. That is bad. There is no reason. That is not that interesting of a question, and I don't think that topic of symptotic series and all of those stuff is big enough to have its own homework. So this week you will not get, but next week you will get. Okay. So what you will do in that case? How do you solve that? Yeah, e to the s. And why it's valid to do that?
Why not?
Yeah, okay, of course, why not? But because it has irregular singular point
Okay.
when
It's infinity.
z approach infinity. But here we need to be careful. We have two parameters that approach infinity. Okay, we actually will take z to approach infinity not in absolute value, because Stokes line is a real phenomena. So we can't do that. But we now need to talk about the relation between lambda and z. They're both approaching infinity, so we need to choose which one is the fastest. And in this case, because it's something we did not do before, it will appear mostly by the end of the course. I will assume that is the real axis, that is the imaginary, and here let's look on something with constant radius circle. And I will say that I want z in absolute value to be much less than lambda. That means lambda is here, infinity, z it's here, and 1 is here, z in absolute value. Z in absolute value is big number, approach infinity, and lambda is here, is much bigger than z. So it's actually interesting to talk about that asymptotics, and we can see easily that the width of the function, what is width? We talked about it in a couple of tutorials ago, but you will talk about that in lecture, don't worry. It's just now a nice trick that I will do that will look like magic, that I take it and got nice stuff. You can see that balancing that, what will be a small number that is here? Small number, let's call it delta, will be 1 over lambda. Because here there is balancing of lambda squared and z squared, so intuitively I can just take that one, that will be lambda squared, that will be that thing squared, and z is a variable, so it can be, but 1 over lambda is a small thing, and if we will take the square root out, you get that thing, and you can see that, okay, maybe changing variables or something like that will be something nice, because, for example, doing 1 over lambda squared, right? We can write the derivative. Let's write t as lambda c, and now we will note that with dots. That will be exactly t squared plus 1 y. So you see, I got the behavior of the function. We know the solution will be in terms of t. Solution will be y of t, which is just saying that is z to lambda. So when you see something like that, you can do a very nice trick. If you don't want to substitute the variables, that is okay, totally okay. Okay, so if you don't want to do that, because I didn't do that when I wrote the tutorial, and let's do that, you can substitute e to the sum of s0. I know that if I will take the 0th order of that thing, I will get just cosine or e to the lambda z plus minus, right? So I already put lambda here, and I will put here Sn and lambda to the n. Why I put lambda here? Because the first term has lambda and I don't want to deal with that in next order, so okay. So you substitute that. Do you want me to do that asymptotics, or I can give you the final result, and we will analyze it and say goodbye.
The final percent.
Let's do that. I have that in my lecture notes, the solution to that thing. That is, if the assumption of lambda is much bigger than z, you get eventually, take my computer, actually a very e to d plus minus lambda z plus minus plus z to the 3 6 lambda plus 6 lambda to the third minus plus z to the third power plus minus plus z to the fifth power divided by 40 lambda squared. And this time I didn't check me numerically, so not sure if I did all calculations right. You see there is a lot of terms and it's a pain in the ass to do that extremely when you're doing that in 3 in the morning, because you wasn't pay attention and you find that you found to S3 for some reason and you continue automatically. Yeah, that is the real reason you have that long expression here. I literally wrote that to the S3, that is S0, S1, S2, S3, and then I was like, wait, that thing not look like it converge with Z. You say lambda is constant, and you take in that summation, that it's not looking like it's converge. But the interesting stuff is when lambda is much bigger, you assume that lambda is much bigger than Z. So all of your assumption and limits need to take that into account, that actually you're dealing with asymptotics of that thing. And that thing is actually approaching 0. Yeah, because we assume that relation. So actually, maybe a nicer stuff to say is our solution is valid in this region. Not far enough, not too far, but not too close. That is very interesting stuff, in my opinion. You sometimes want to catch some behavior that occurs between two parameters. So two constants, 1 and our lambda. And when we are taking more and more terms, we're getting more and more accurate approximation. But what is true? Z, it's okay, it's very large, but it's not infinite, because it's less than lambda. So those actually are corrections. I summed the correction because one of the corrections had something like z to the 5th plus lambda something z to the 4th. Okay, don't mind. I don't care about those stuff, right? It just, when I wrote it and sum all of the correction, that is S0, but that thing is not S1, okay? Just to clarify. But we actually got corrections. And in my opinion, it's very nice. Analyzing the Stokes phenomenon where it's valid, because actually I a little bit lie to you. Why? Because it's not valid everywhere. Here, our asymptotics, if we want to choose just one of the solution, let's say the plus solution, it will be valid only here because of Stokes phenomenon. Why? Our Stokes line, that is phi of z, right? The other stuff is a of z, and the Stokes line is crossing here. And where it will be the best to approximate? At the real axis, right? So in that region, small region, it will be the best. And if you want to do the best correction around that, you say, okay, z is equal to re to the I theta, right? But theta is very small, so what you actually need to substitute is r plus what? 1 plus I theta. Then you substitute, and when you will do the numerics for real plane to prove that thing is valid, you will get the best result and best matching. Right? So it's another tool to verify yourself. It's nice to remember. Okay. I think we are fine. We finished. Unless you have some questions.
I think we actually finished. Oh.
Yeah, I finished all the tutorial. It's 16 pages. And they said everything I want to say. So, yeah. בסדר?
כן, כן, היה פצצה. זה נושא מעניין, הוא פשוט באמת קצת אנמי.
כן, הוא קצת אנמי, אבל כאילו... שמע, אני אוהב מתמטיקה, אבל אני לא אכנס פה לקונספטים מתמטיים תיאורטיים.
כן.
אז מה שאני כן אמרתי, זה אמרתי, אוקיי, אם כבר יש לי תרגול מאוד מתמטי, אז בואו נכניס קצת פונקציות שמופיעות מדי פעם בקורס או בכל מיני מקומות, וכל מיני ביטויים מופצים שזה נחמד, אני אוהב את זה.
בוא אני אשאל את זה ככה, במבחן, מה...
הביטויים האלה מופיעים לך מלא במבחנים.
באמת?
כן, אבל זה סתם ביטוי מתמטי. אם תרשום את בסל פונקשן, אתה עושה בשנייה התמרת פוריה, ואז אתה מקבל את האינטגרל, אז האינטגרל של החזרה של פוריה הוא עם פקטור של 1 חלקי שורש 2 פאי. הטנגנס תטא זה סתם פרמטר שאתה תקבל, אתה ממש תראה את זה מהר.
יש לזה שימושים בפיזיקה עצמה? אתה רואה את זה במקומות בפיזיקה או שזה רק במתמטיקה?
לא, פה, אוקיי, כמובן שמה שאתה עושה פה עכשיו זה מתמטי, אבל אם אתה רוצה סביב נקודה מסוימת לדעת איך משהו מתנהג, הנה קיבלת. יש לך פה חופש, יש לך פה פרמטר, תטא. זה יהיה לכל תטא כש-v שואף לאינסוף. אז יש לך עוד חופש של הזווית כביכול. אתה רוצה לחשוב על זה ככה. אז עשית על זה approximation, למעשה לבסל פונקשן בתחום כזה. אתה יודע את הערכים ואיך זה יתנהל. ולא יודע, לדעתי זה מעניין. וכאילו ה-corrections, אני לא בטוח אם הם תלויים בתטא או לא. לדעתי הם אפילו לא תלויים בתטא, אז כאילו זה עוד יותר מעניין אם אתה שואל אותי. כי זה לא אינטואיטיבי לפחות לי, שהנה, קיבלתי את כל ההתנהגות בתטא וזה עכשיו רק קבוע, ואם אתה מתעסק בקוונטים, תנרמל וניצחת. יאללה.